The superactinides are a series of unknown elements that take place beyond our known periodic table, and so their electron configurations are unknown. But how can we find them? And is there a rule to determine all future electron configurations? Before we can predict future electron configurations, we must understand how to find the known electron configurations. There are three main principles which dictate these configurations: the Aufbau principle, the Pauli exclusion principle, and Hund's rule. The Aufbau principle states that electrons will fill each subshell in order from lowest to highest in terms of energy. This is because an atom's most stable electron configuration is the most favorable. The Pauli exclusion principle states that there can be at most 2 electrons per orbital, and 2 electrons in the same orbital will spin in opposite directions, since the negatively charged electrons will repel each other. Hund's rule states that within a subshell, 1 electron is located in each orbital before they double up. Furthermore, electrons within a subshell will be configured in such a way that maximizes the number of electrons with the same spin. In addition to these three principles, Madelung's rule expands on the Aufbau principle to establish the order of the subshells by energy. Madelung's rule uses the following diagram to determine the order of subshells. While Madelung's rule sets the standard for how electrons are arranged, there are many irregular electron configurations that break this rule. The first notable irregular trend occurs in groups 6 and 11, where the following elements have a d subshell that is either half or fully filled. This increases the stability of these elements because the symmetrical distributions of electrons is more ideal. Another trend occurs in groups 5 and 10, where the following elements have an electron moved from their s subshell to their d subshell. However, the most interesting trend comes in the lanthanides and the actinides, where a pattern is developed. Beginning with the 4f subshell, the lanthanides, the series begins with lanthanum, which has the electron configuration of xenon 6s2 5d1. This breaks Madelung's rule, as the electron in the 5d subshell is predicted to be in the 4f subshell. Next, cerium has an electron configuration of xenon 6s2 4f1 5d1. An electron remains in the 5d subshell, continuing to break Madelung's rule. Next, praseodymium has its expected electron configuration of xenon 6s2 4f3. The elements neodymium, promethium, samarium, and europium all have their expected configurations. However, gadolinium has the electron configuration of xenon 6s2 4f7 5d1, where an electron reappears in the 5d subshell. This is because gadolinium's half-filled 4f subshell is very stable. Then, all of the lanthanides following gadolinium have their expected electron configurations. There is a hidden pattern in the irregularities of the lanthanides. When the number of electrons past 6s2 exceeds multiples of 1/5 of the capacity of the 4f subshell, which is 14, a transfer will occur from 5d to 4f if possible. For example, praseodymium has 3 electrons past 6s2. Since 3/14 exceeds 1/5, praseodymium is a transfer point. Since there is an electron in the 5d subshell at this point, a transfer occurs. 1 electron moves from the 5d subshell to the 4f subshell. At samarium, there are 6 electrons past 6s2. Although 6/14 does exceed 2/5, there is no electron in the 5d subshell at this point, so there is no transfer to occur. At terbium, there are 9 electrons past 6s2. Since 9/14 exceeds 3/5, terbium is another transfer point. Since there is an electron in the 5d subshell at this point, a transfer occurs. 1 electron moves from the 5d subshell to the 4f subshell. At erbium, there are 12 electrons past 6s2. Although 12/14 does exceed 4/5, there is no electron in the 5d subshell at this point, so there is no transfer to occur. At ytterbium, the 4f subshell is full, so there is no transfer to occur. The same trend occurs in the actinide series, with the same pattern dictating the transfer points. However, in the actinide series, there are 2 electrons that appear in the 6d orbital as opposed to 1. As a result, there are transfers at protactinium, plutonium, and berkelium. There are a few electron configurations that are anomalies without a trend that continues throughout other elements. In order to predict the unknown electron configurations after Oganesson, we can use previous trends to find the irregularities and we can use quantum calculations to find configurations with the lowest total energies. Starting with elements 119 and 120, they fill up the 8s subshell with the following configurations. Next, the 8p subshell splits into two parts due to relativistic effects, causing elements 121 and 122 to fill up the 8p 1/2 subshell. Next, the elements 123 to 140 are within the 5g subshell, and there are many possible configurations. If we order configurations by lowest total energies, then the following configurations are applicable. However, if the 5g subshell follows the same trend as the previous f subshells, then there may be transfer points from the 6f subshell to the 5g subshell. If such transfer points occur in fifths, then the following configurations are applicable, with the transfer points in blue. However, if the transfer points occur in sevenths, since the f subshell has 7 orbitals as opposed to the d subshell's 5, then there's a slight adjustment for element 125. Next, the elements 141 to 154 are within the 6f subshell. If we again order configurations by lowest total energies, then the following configurations are applicable. However, if we again apply this trend from the lanthanides and the actinides, then the following configurations are applicable, with the transfer points in blue. Additionally, here are the configurations if the two are blended. Yet there's one more question that can be answered. Why do the transfer points occur at these intervals? Well, it may have to do with where the electron is transferring from, specifically the orientation. When electrons transfer from the d subshell to the f subshell, there are 5 d orbitals in which electrons are transferring from. If each transfer point occurs in multiples of fifths, then there are 5 transfer points throughout the f subshell. Could each transfer point be connected to a specific orbital? This would not contradict Hund's rule, since Hund's rule only states that all orbitals must have 1 electron before doubling up. It is not stated that the orbitals must fill up in order, since each of the d orbitals within the subshell have the exact same energy, as they are perfectly symmetrical. Hence, neither Hund's rule nor the Aufbau principle is violated. So, for the 6f subshell, there's a transfer from the first 7d orbital to the 6f subshell at element 143. There's another transfer from the second 7d orbital to the 6f subshell at element 146. An electron reappears in the third 7d orbital at element 148 to maintain the half-filled 6f subshell, and that electron is transferred to 6f at element 149. The 6f subshell then fills up as expected. Next, elements 155 to 164 fill up 7d subshell, with a potential irregularity at 162 due to the trend in group 10. Lastly, elements 165 to 168 fill up the second part of the 8p subshell, 8p 3/2. And there we have it, the predicted electron configurations of the superactinides. While we cannot know for certain if these are correct until discovering these elements, we are able to make these justified predictions with what we already know. There are other theories, some that believe that subshells such as 9s are filled earlier than expected due to further quantum corrections. Hopefully these elements do exist, and these electron configurations can be discovered. Thanks for watching, like and subscribe.